My name is Shoumik. I'm a fourth-year PhD student working with Matej Zaharia, and I'm going to talk about some work we did on hosting online applications yourself for online privacy. So when the internet was first conceived and its protocols were designed to be a federated system. So organizations and users of the internet would host their own email and chat and file transfer servers, and by extension, they would also end up managing their own data. But today, we live in the era of centralized services. So what I mean by this is that centralized services store data for an organization, and organizations kind of trade control of data in exchange for things like high availability and low cost. So as a few examples of this, you store your email with Google, and Google ensures that your email server is always going to be up. And kind of the same thing applies for a chat service like Slack, or for your documents in the cloud in applications like Office 365. So on the one hand, this is great because you get high availability at basically zero cost. You get to run your email for free. But then you also see news articles like this popping up every now and then. Right? So here an ex-Googler was spying on people's user emails and chats just because he worked at Google and he had access to all this data. Here, this app called Unroll Me, which claims to clean up your inbox by going through your emails, was found to be selling your data to Uber, and Uber was using it to get tips on like what Lyft was doing. So that's not great because you were not expecting this application to kind of sell your data to other companies. And this is probably the worst one. So in Germany, they had these smartwatches that were meant to track your kids around when they're going to school and make sure that they're safe. But it turns out that the web service that was running this service was open to basically anybody. So it turns out that people were kind of following kids around, and there were obviously some significant safety concerns with that. So Germany just banned these smartwatches altogether. Okay, so if we have these kinds of privacy issues, then why do we actually rely on these centralized services? And as I mentioned before, kind of the main reason for this is that they do provide high availability at a low cost. And by high availability, I mean things like failover configuration. So if one of your servers fails, Gmail is not going to go down if like one disk fails in Google's data center. You get things like geo-replication. So if there's a tsunami here, you can still access your email via a server in like Europe or something. And you get things like auto-scaling, so you can handle things like bursts of requests, and many more things of this nature. So if you think about what it takes to actually self-host a server yourself and also get all of these things, it's not exactly cheap. Right? So the strawman is kind of hosting your own tiny EC2 VM, and kind of the smallest instance type here costs around $450 a month. And if you want to do things like high availability, this obviously costs even more. Right? So if you want to geo-replicate this VM in Europe or something, this cost will double, and then you have to pay even more for things like auto-scaling and automatic failover reconfiguration. Okay, so it seems like there's no way to get high availability, low cost, and privacy via hosting your own services at the same time. But there is a new hope, and that's this paradigm of a serverless computing. And serverless computing is basically this promise of the availability of a top-tier cloud service, but with no cost when the service is idle. Okay, so the way that serverless computing works is that you basically install these little functions in the cloud, and they only execute when you actually make a request to them. And they're billed at a very fine granularity. So when you run a function, they're only billed on like 100 millisecond granularity. Okay, and if you look at how this scales in terms of cost and requests for these kind of personal applications like email and Slack, for example, for EC2, there's some fixed cost for every instance that you configure. So even if you're making like hundreds or thousands of requests a month, you're paying the same amount as you would when you're making like millions of requests a month. But with these serverless functions, most users are actually going to be on the left side of this blue line here. Right? There's going to be a pretty significant gap of the amount of requests you're making for something like a chat server, and the amount of money you have to pay to configure one of these VMs. So deploy it yourself, or DIY, is this idea of users running their own personal web applications using these serverless computing platforms. And the goal of this is to achieve high availability, low cost, and privacy all together for the first time since the heydays of the internet. Okay, so I'll quickly go over the high-level architecture of DIY. So our prototype and kind of our initial design of this actually just stitches together a bunch of existing cloud services. And I'll talk about how we can actually make this more secure than what you can do with existing solutions a bit later in the talk. Okay, so cloud providers provide this serverless platform, and kind of the first thing you have to do to set up DIY is register a serverless function. Okay, so this function is basically a proxy for like what your web server would be. So it would register like a message into a chat log, or act as an email server, for example. The next thing you do is configure a cloud storage provider. So this could be something like Amazon S3, and this is where you store your encrypted user data. And this is kind of where the security comes from. Instead of giving your data off to one of these centralized services, you encrypt it with some key and you store it in some public cloud service. And assuming that the storage service isn't secure, the provider can't kind of read your data just because it's encrypted by some key. Okay, and then finally you register a key with a key service. And I'll talk a bit about why it makes sense to kind of trust this key service and not centralized services or these other storage services that we're kind of not trusting. But this key service is basically the secured place where you can put a private key and then use an API to retrieve that key and then decrypt your data. Okay, so once you've kind of set up these three things, clients make requests to a web endpoint as they would always. And the serverless platform kind of behind the scenes would load balance these requests and invoke these serverless functions. So each function would then call out to this key service, grab the key using some signing mechanism, and then use that key to decrypt the data in your storage service, and then you would process your request and send a response back to the client. Okay, so that's kind of the 1,000-foot view of how the architecture of this works. Okay, so why is DIY actually more secure, right? We're still depending on all these kind of cloud services. So why is that better than trusting Google with Gmail, for example? And there's kind of 4 high-level reasons that I'll discuss. So the first reason is that the boundary between the data that's unencrypted and the service that you're trusting is very narrow. Okay, so if you look at a centralized service, there's many internal systems, database indices, ad targeting systems, all these kinds of things that you're implicitly trusting by giving your data to, this centralized service. But in this system, your data is basically only unencrypted within this kind of container that's running your Lambda function or your serverless function. So the boundary between where your data is unencrypted and where your code is actually capable of exfiltrating data is very narrow. Okay, the second kind of point is that stored data is encrypted to prevent leaks. In a centralized service, employees access data to monetize it, right? They train models over them and they, again, use them for things like ad targeting. Here, your data is encrypted in the cloud service, so you basically can't read it for that reason. Okay, third, this is kind of a soft reason, but cloud providers are kind of incentivized to minimize data access internally, right? So if you look at a centralized service like Google or Facebook, when you're using Facebook Messenger or something, the user agreements actually state that data can be used for things like ad targeting. And you very clearly see this. If you talk about dogs or something on Facebook Messenger, you're going to start seeing dog collars in your Facebook feed. On the other hand, the cloud providers are kind of providing a different kind of service, right? They're kind of trusting you to run your web services and applications, and kind of the guarantee that they make is that you're not going to get hacked and your data is not going to be exfiltrated. So they're just incentivized to minimize access to your data by like employees and things like that. And finally, with DIY, you also have the ability to migrate your data off things like insecure clouds and regions. So if you read in the news that some particular region or some public cloud that you're using to host your service is insecure, you can just download your encrypted data and move it somewhere else. And this isn't necessarily easy to do with other services, especially a lot of it is dictated by the laws of particular regions and things like that. Right, so in a centralized service, you generally have no control over where data lives, although this is slowly changing nowadays. Okay, so there are, of course, some assumptions that we make here. And in particular, we assume that the function code, the isolation mechanisms that are actually running the function, and the key service are trusted. Okay, so diving into that a little bit deeper, I'll talk a little bit about what's actually trusted in this system and what's not trusted. Okay, so the first thing that's trusted is the serverless computing platform, the isolation mechanisms of the serverless computing platform. So the function containers that are actually executing the code must hide the function execution end state. Right? If your cloud provider is capable of kind of reading the memory of the function that's running your server, then you're out of luck because they can just read the unencrypted data while the function is processing it. Okay, and I'll talk a little bit about how things like enclaves can kind of secure against this as well, though I don't think any public clouds actually support that yet, but maybe they will one day. Okay, yeah, so you could one day maybe test this stuff with hardware enclaves. So the second thing that you trust is this key management service, which is responsible for protecting access to user keys. And I think the reason it makes sense to trust this key management service is because its kind of only job is to store these private keys securely. And they're already implemented in things like hardware enclaves. If you look at how Amazon secures these keys, they already use these hardware devices and hardware encryption to protect them. And they're also heavily audited by third parties, for example. So this is obviously not going to protect against things like the NSA, but I think it's reasonable to say that a key management service whose job it is to encrypt your encryption keys is more reliable than a scanning system at Google for. Okay, so again, management services already secure these things via enclaves and enclaves today, and they also have things like strict user agreements. Okay, and the final thing that we have to trust is the function code itself. So if the application you're running is going to scribble all your data onto Facebook or something, we can't really do anything about that. So the function code can't leak data or have critical bugs. Okay, so what's untrusted? We don't trust the internal network of the cloud provider. We don't trust the storage service and any other cloud service for that matter. We assume that all their data will be encrypted in motion. And we also don't trust internet traffic between the user and the cloud provider. So that's something you could handle with standard mechanisms like HTTPS or TLS. Okay, so going back to this 1,000-feet view of DIY's architecture, the yellow components are the ones that we're trusting. And I just want to reiterate this. Each of these are kind of simple enough that you could maybe one day secure them via things like hardware enclaves. And enclaves are kind of like the standard mechanism that people are looking at for securing code execution in the public cloud today. So the key service, as I said, is already secured via enclaves in many public cloud systems, and maybe one day we'll see function execution secured via these mechanisms as well. Okay, so what does DIY actually protect against? I'll go back to some of the problems that I discussed earlier. So against snooping employees, DIY does help against this because they don't have access to your executing functions, and at rest, your data is encrypted. For the same reason, we can protect against things like data mining and sale just because the cloud provider can't access your data. Buggy or insecure software, we can't protect against this in all cases. If your application is kind of explicitly malicious or buggy, then there's nothing we can really do about that. But we also can protect against some classes of bugs. And the reason for this is that cloud providers generally provide some mechanisms for setting the permissions of certain services. So you could potentially set up some kind of whitelist or blacklist of places that a function can make calls to, for example. And I'll talk a little bit more about this at the end of the talk. But we kind of protect against this and we kind of don't. It kind of depends on how the application is set up. And things like government surveillance, we're not using any fancy cryptography or anything here, so we can't really protect against this. If the NSA goes to Amazon and says, give me Shoumik's keys, they're probably going to do that. But I probably also have bigger problems in that case anyways. Okay, so in the rest of this talk, I'm going to talk about some prototypes that we built that kind of demonstrate that this system works end-to-end. So first I'll talk about some back-of-the-envelope costs for how much it takes to actually deploy this and run it in a public cloud today. Then I'll talk about a chat prototype that we built and some challenges that we faced with that. And finally, I'll talk about a potential marketplace for DIY applications, where application developers can kind of run their applications in the public cloud, but each user would manage their own data for it, which could potentially lead to a more secure internet because people are, again, federating their data as opposed to trusting these centralized systems. Okay, so in terms of cost, we basically analyzed a few common personal web applications that people would want to run in this system. And we basically looked at some back-of-the-envelope numbers for various parameters of each of these applications. So we looked at the number of daily requests we might expect, the amount of time it takes to compute per request. This is important because the functions are billed by millisecond, as I said before, or by hundreds of milliseconds. The memory the application would need, and also the amount of persistent storage that the application would need. And if you look at the rightmost column here, most of these applications need like a dime and a quarter to run. The exception is video chat, and we actually tried the video chat one on a build per second VM. So we spawned a VM, and then we basically computed how much the VM would be billed for the duration of the video chat. So again, I want to remind you that the kind of comparison point here is a single unreplicated EC2 instance, right? So without this, you don't get things like failover or geo-replication or any of these great high availability features. And it also costs $450 a month to always have this thing running. So it's orders of magnitude more expensive than relying on these serverless platforms for applications like group chat and email and file transfer. So we also built an actual chat prototype to see what the challenges of building this with current cloud infrastructure was. So the prototype is pretty simple. We basically registered an HTTPS endpoint on Amazon, and that endpoint will spawn serverless functions when you send messages to it. And then the function will use the key service to get the key. It'll write an encrypted message to the encrypted storage, and it'll return back to the user. Okay, but there were kind of two challenges with building this chat prototype. The first one was asynchronous communication. So in this diagram that I've shown here, clients are basically sending messages. But to receive messages, we don't want to have a Lambda that's always running, because that kind of defeats the purpose of using these serverless platforms in the first place. So we kind of hacked together a solution for this. What we did was that we used this queue service that exists in Amazon to basically have the serverless function write messages to a queue, and then the client would pull from the queue. And the reason that this works is because these queue services, and a lot of these services in Amazon, are actually built for these kind of high throughput, high volume applications. But because we're kind of using these for like personal web applications, the kind of expected throughput is so much lower than what Amazon would expect you to use them for that they end up being free. So we can basically pull this queue all the time and not have to pay anything. The second challenge was the latency of posting a message and then receiving it. So we actually found that the latency of writing data to this encrypted storage was pretty slow, as was actually writing data to the queue. And we kind of just, again, hacked together a solution for this. We found that appending smaller objects to S3 gave us better performance than appending big objects, and also that allocating more memory for the serverless functions somehow changed the SLO in the backend or something and gave us better latency. So end-to-end, to send a message and then to receive it at a different client, it took around 200 milliseconds, which isn't fantastic, but I think with maybe some more engineering, we can get this down even further. And most of the time is actually spent, as I said, in reading from the SQS queue and posting to S3. Okay, so the nice thing about this is we can actually send 25,000 messages a month with zero cost. So Amazon has this free tier for a lot of these services, and 25,000 messages is nothing for these services that are supposed to drive these kind of cloud services, right? So for basically paying nothing, you can send 25,000 messages a month. So this includes the queue, the Lambda cost, the key management service, and all that stuff. For an additional 9 cents per month, you also get storage. So this is assuming you're storing 5 gigabytes of data, which is a lot of chat messages. Okay, so the last thing I want to talk about is how we can bring these DIY applications to everyone. And so this is largely ongoing work. But if cloud providers are basically able to provide a platform that treated these applications as first-class citizens, they could potentially do things like installation and permissions and signing of applications and handling updates and so forth. And this has a bunch of advantages. So for the users, I basically spent the whole talk talking about what the advantages for them are. You basically get privacy with, again, automatic low cost and availability. But it has some pretty significant advantages for developers too. And that, in particular, is faster innovation because you don't need to manage a full multi-tenant scalable service. So if you think about an application like Slack, for example, think about what you have to do on top of just building like the Slack UI and like the application features that everyone actually sees, right? You have to manage everyone's data. You have to make sure that your service is up all the time. Slack is actually down pretty often if you think about it. And you also have to make sure that everyone's data is secure and that people are able to delete their data, manage accounts, all that great stuff. With a system like DIY, a lot of that stuff would kind of go to the cloud provider who are experts at kind of doing all this stuff already. And developers will be able to kind of focus on features and innovating on their actual products themselves. So we think that it's actually an exciting opportunity, even for like enterprise applications who might not care as much about cost, but may want to manage their applications using some third-party service. Okay, so to conclude, DIY could really revolutionize how we run web applications by offering privacy, high availability, and low cost for the first time. So if you want to read more about this work, it was published at Hotnets 2 years ago in Hotnets 2017. My email is up there if you have any questions. Thanks. That's right. Yeah, I think so. The question was, Lambda has all these limitations, basically, that would make it hard to handle real applications with like user sessions and stuff. I mean, that's a great point. I think this is more of a prototype that shows that if serverless were to become more mature over the next few years, this kind of thing could be used to run some real applications. I think the billing model since we did this work, the billing model for a lot of VMs has also changed, so that it might also be possible to kind of spawn full-fledged containers or virtual machines to do this kind of stuff as well. But definitely you can't run like full applications on Lambda today. It's probably too limited for that. Mm-hmm. Yeah, so the way the SQS thing works is you basically like write to a HTTP endpoint. So I think even a browser would be able to do it, but it's not very elegant. Yeah. Yeah.
So what is the exact rationale behind this leap of faith of trusting the Amazon infrastructure? Mm-hmm. I mean, you don't even know where it is. So how is this not an arbitrary decision?
It's not arbitrary just because of the components that we're trusting. So I talked a little bit about the key management service being, run in enclaves, for example. And the other point is that the actual code that's running, again, has like a fairly small attack surface compared to these centralized services.
But Amazon runs these machines in place unknown to you. Mm-hmm. Why do you trust their hypervisors? What's the rationale?
So I guess the rationale for trusting the hypervisor right now is that we really don't have a choice if you want to run them in the cloud. Yeah, it's not a great reason. But eventually, I mean, like I said, like a lot of these things could actually be, secured via enclaves or things, in which case you don't actually have to trust the hypervisor. But today, if you were to use any public cloud, you basically have to, trust the hypervisor in that case anyways. So there's really no getting around that. All right, let's thank Shoumik one last time.